So if we think about the reaction force of the sine, this is a little bit different now because, we have the sine that, you got a force coming down like this, but then you have this, kind of force coming up like this that we're looking at. And so in this one, and then, something's happening down here, right? And so we have to consider all of those things. Let's say that we have a beam that's being held here, and this part right here is free to move. This is a line of tension holding this beam up. So if this snaps, this is just going to fall down like this. Let's say the mass of the beam is 150 kilograms, and we want to find out what the tension force is here, how much force of tension there is, and then also what's happening over here, because there's a wall over here, and then this is this is going to certain amount of force is going to be felt over here. So again, the hinge is free to rotate. If it's not, then this wouldn't be, the value that we're going to get over here wouldn't be the same as if it wasn't free to rotate. We have the force of gravity of the beam there. We have the force of tension over here. And we have some sort of, wall force, reaction force, we're going to call it over here. And that's part of what we're going to find out. We want to know what tension is. We want to know what the reaction force is. And we actually don't know either. So we're going to use, what we can do here with the forces and the torque to figure out what's going on. So we're going to break down the reaction force and the tension force into the x and y so we can get it in something that we can use. And we'll set up the sum of the force in the x, sum of the force in the y, sum of the torques. The forces in the x, positive force of reaction in the x plus the negative force of tension in the x. In the y direction, positive force of reaction in the y plus the positive force of tension in the y plus the negative force of gravity. And then for your torques, we're going to use the rotation point as right here is the hinge. We could technically have used, this over here and then use that as a rotation point, but it's a little bit more intuitive to use the left-hand side. And so in terms of setting up the torque, right, we have force of tension in the y, which is over here. And if we break up the force of tension is located right here, right? We're just breaking in the x and y components. So that y tension is right here. So we've got that. And we have the force of gravity. So we can actually solve for what force of tension the y is. We'll, 1/2 x is how far the force of gravity is of the beam. We can cancel x from both sides. So the force of tension the y comes out as 1,470 newtons. Now, if you notice here, this angle, theta, is 30 degrees. So because we know that, we can figure out what the overall force of tension is. We have, this is right here, force 1,470, and we know the angle, so we can use trig to find the hypotenuse, which is the force of tension. And we can set that up with, oh, that's right. No, I'm sorry. We are, if you put this in terms of force of tension as the sine of 30, we actually already did that. So that is the force of tension. Sorry about that. So the force of tension here is, what we found. If you just left this in FTY and then solved for it, you would have gotten a different value. And this has the trig already in it. So I figured I did that. And that's usually how you'll set it up. Once you find that force of tension, to get the FTX here, right, you have the hypotenuse, which is 1470, and you're looking for the FTX, which is the cosine equals adjacent over the hypotenuse, so the cosine of 30 equals the adjacent side over 1470 cross multiply, so we got that, right? And so the reaction force in the x is 1,273.1. And now that we know that, we can look at what's going on in the y direction. We know what FRX is, and force of tension in the y we're going to place in here, which is the hypotenuse times the sine of 30. And we can figure out the force reaction in the y. So now that we know the reaction force in the x and y, we can use the Pythagorean theorem, set up our coordinate axis, 1273.1 newtons in the x, and then 735 in the y. Opposite over adjacent to get the angle 30 degrees north of east, 1470. And this will be true as long as there's nothing on the beam. It'll actually be the same, and that should make sense because the tension is has to be completely canceled out by the other side so that the equilibrium is reached there. Now we're going to consider this overhang right here, and you can see that let's get into color. You can see that this is held up here by these different support beams, and this is again a static situation where all the forces are balanced out, and this isn't rotating down, right? If this was gone, this would just fall down like that. So we're going to take a look at that situation now. So here's the factors here that we're going to look at. We've got a beam that's 5 meters long. It's 300 newtons, and the cable's 53 degrees. And there's a worker standing 1.5 meters from the wall hinge. So just like we saw in that picture, this is a similar situation where we have this being held up here by a wire, and it's a static situation, but it's in an angle. If you notice in that picture, the last picture, it was in an angle. This is 53 degrees here. So we follow a similar process to what we did before. We'll set up our forces. So we have force of gravity of the man, force of gravity of the beam, the force of tension, the reaction force of the wall. We set up some of the forces in the X, Y, and torque as well. And our goal in this problem is to figure out what the reaction force is and what the tension force is. Now in this case, we have an added dimension that there's a person standing here. So in this case, the reaction force and the force of tension will not be the same, because the man is standing close to the wall there, where this hinge right here is free to rotate, and the reaction force is going to be able to have to hold up more because of this. So that's what we're going to analyze in this one. So what I want you to do is go ahead and write out some of the forces in the X and the Y. You're going to have to break down the reaction force, break down the force of tension into their components, and write those out, and some of the forces of the X, some of the forces in the Y. And then with torque, go ahead and write out the torques as well, and whether they're clockwise or counterclockwise. And once you do that, go ahead and play the clip and make sure you've got that before we move forward. So go ahead and pause the clip and try that, and then when you're ready to check, you can hit play to continue. Okay, so break up our reaction force in the X, reaction force in the Y. In the X direction, positive reaction force in the X plus the negative force of tension in the X equals 0. In the Y direction, we have the positive force of tension in the Y, positive reaction force in the Y, plus the negative force of gravity of the beam, negative force of gravity of the man. And the torques. So if we chose, over here is the hinge point, we have the positive FTY, so tension, right, is going to cause a counterclockwise rotation, so it's positive. The negative torque of the man, that's got a clockwise torque, and then the beam is a clockwise torque as well. So now that we have that set up, what I want you to do is go ahead and tackle this part here in variable form and see if you can figure out what the force of tension is. And then once you've done that, you can hit play when you're ready to check. So go ahead and hit pause and work through that, and then hit play when you're ready to check that. Okay, so we have the force of tension times the sine of 53 times 5. It's 5 meters long, so that's where the tension is acting right here. So it's 5 meters from here. Force of gravity of the man is 1.5 meters, and then the force of gravity of the beam is 2.5 meters right in the middle. And our force of tension should come out as 413.205 newtons. So now that we know that, we can go ahead and we'll go ahead and move to the X. And so go ahead and try that. Go ahead and work through and get the reaction force in the X. And why don't you go ahead and try the Y as well. Once you get you can solve for the force of tension in the Y. Now that you have the overall force of tension, right, you got this, you can set up your right triangle, figure out what the Y is here, figure out what the X is here, and yeah, see if you can get those. And then once you solve for the reaction force in the X and the reaction force in the Y up here, you can set up your triangle and see if you can find the overall reaction force. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. Okay, so place that in there. We know that the force of tension, the x-axis, is the force of tension that's cosine of 53 to get the adjacent side. 248.67 should be what you've gotten in the force of reaction in the x. In the y direction, we should get the force of reaction in the y5, 69.9998. And when we set up our Pythagorean theorem there, the x and y for the force of reaction, we should get 621.88 newtons at 66.4 degrees. So the adjacent over the hypotenuse tangent, inverse tangent of opposite over adjacent, rather. Opposite side over the adjacent, inverse tangent, so 66.4. So if you notice the tension force, right? The tension force is 413 at an angle of 53 degrees. The reaction force is 621.88 at 66.4, right? So the reaction force is greater over here because the man is standing over here, which should make sense. And it's pointing upwards a little bit more because it's counteracting the force of gravity of that man. Now let's consider this traffic light. This is another static situation where this traffic light's being held up by this beam right here, and then there's a couple tension wires that we're looking at. So let's say that we have a beam that's 400 kilograms. The mass of the traffic light is 23 kilograms. Line of tension is 4/5 of the way down for the cable here, and we know that this angle right here is 25 degrees, and we want to figure out what's going on. So this is similar in the fact that, this is free to rotate, we'll say, this spot here. And, if this tension line is cut, this is going to rotate down. And in this case, the right tension is not all the way at the end. We have the traffic light all the way at the end. And in this case, you're not given actual lengths. So for this one, you actually have to use relative lengths, L being the full length here, and then you have to consider the other ones, what those would be. So, we've got the force of gravity of the beam there, reaction force, tension, force of gravity of the light there. So what I want you to do is go ahead and set up the forces in the x, forces in the y, and the torques. And let's do that just in variable form, and then you can check your progress. So go ahead and pause and do that. And then when you're ready to check that, you can hit play to check it. Okay, so reaction force in the x plus positive reaction force in the x plus the negative force of tension in the x. Positive force of tension in the y, a positive reaction force in the y, plus the negative force of gravity of the beam, negative force of gravity of the light. And then for the torques, the light will be a clockwise torque, right? If we use this as our axis of rotation, clockwise. And again, you don't have to use this as the axis of rotation. You could use this and then base everything off of that because you would eliminate another variable. But, right here, it just seems more intuitive to me. I'm just more used to that. So, but it's up to you. So in this case, reaction, there's no torque caused by the reaction force because it's right, it's located at the axis of rotation. So we have the negative torque from the light, the positive torque force in the y, force of tension in the y. So this is a positive torque counterclockwise, and then the beam is a clockwise torque, so it's negative. So on this one, what I want you to do is go ahead and work this one all the way through. Go ahead and, for the tension here, you're going to have to put things in relative to L. So yeah, let's actually do that. So why don't you go ahead and solve for what the force of tension is in this part, and then you can check your progress because it'll make sure you got that before you continue on. So go ahead and hit pause and try that, and then when you're ready to check, you can hit play to continue. Okay, so we have x, and then 4/5 x, and then 1/2 x. You could have used L as your variable. Either way is okay. So the light, right, is the full length. The tension in the y is 4/5 of the way, so it's right here. Told you that. And then the beam is halfway, right? So we can divide by x from both sides. And we'll end up getting a force of tension here of 6,463.87 newtons. And so now that we have that, why don't you go ahead and try the forces in the X, forces in the Y, figure out what the reaction forces are, and then bring those together and see if you can solve for the reaction force. So go ahead and pause and try that, and when you're ready to check, you can hit play to continue. Okay, so in the X, we should get 5,958.257, and then in the Y direction, reaction force of 1,413.66. Bring those together, and actually I think that is 5,850. I can read my own handwriting there for a second. 5,858.257 newtons in the X, and then we've got our Y force. The overall reaction force should be 6,026.41 at 13.6 degrees above the x-axis. So in this case here, it's interesting, right? Because the traffic light is actually overhanging where the tension is, but you work at the same exactly the same way, and go from there. Now let's consider the static situation of a diving board. Now let's take a look at a situation where we have a person standing at the end of a diving board, and we'll say here that the diving board is attached right here at FA, and the diving board is resting over this beam right here at FB. And I've got the mass of the person here. We've got the relative length set up. The mass of the beam itself is 110. The mass of the man is 70 kilograms. And the center of mass of this diving board is located right here. And we want to figure out, what's going on with FA and FB. So this one's a little bit different. It is a static situation where, the forces on FA and FB are going to be there, but we want to figure out, what those are, and those are two unknowns, and so we can do that. So the first thing we're going to do is draw the free body diagram. So go ahead and pause the clip, draw this picture out, and then draw where the forces, what you think the forces are doing, and then we'll go from there. All right, so let's see how you did there. We have, the FA, some sort of force here, force B, force of the board itself, and then the force of gravity of the person. So we actually don't know what's happening here with FA or FB. We know though that one might be up, one might be down. One's going to have to counteract the force of gravities here, right? So one of these has to be up. Maybe both of them are up. So that's what we're going to have to try to figure out here. So what we're going to do is we're going to leave FA and FB blank in terms of the signs. We're doing what the signs are going to be. We know the force of gravity of the man, force of gravity of the beam are both negative. So when we set up the torques, we can set up our axis of rotation. Let's go ahead and use that here. So if we do that, we know that the board itself is going to have a reaction force, or not a reaction force. The board itself is going to have a clockwise rotation. The man's going to have a clockwise rotation in terms of torque. So we know that FB must counteract that, right, in the opposite direction. So that must be a negative torque there, or a positive torque rather, while the other two are negative torque. So we can set that up, FB and then the beam and the man. And with just that, we'll be able to figure out, what FB is and what FA is. And so why don't you go ahead and take it from there and find out what both of those are, and then you can check when you're ready. So go ahead and hit pause, and when you're ready to check, you can hit play to continue. Okay, so 2/5 L for FB there, 1/2 L for the force of gravity of the beam, the diving board, the man, full length L, and L will cancel from both sides. And we end up getting 3,062.5 newtons as our force for FB there. Once we know that, we've got our forces there, we're going to be able to find out what FA is. And it actually turns out FA is a negative force, which may be kind of weird for you to see.